I will go through several use cases we are working with big data, not just big data, it's also the application of data-driven models to sustainable energy systems. So if you have if my slide is frozen or if there is any internet connection problem, just let me know, write on the chat or interrupt me. So it will be, I think, interesting presentation, but will be a little bit longer. And if you have any questions, you can raise the hand and interrupt me. Feel free to interrupt me. So I will start with something that in Europe is emerging. And you have here an example. This was a report that was published in 2022. And it's about the data exchange reference architecture. And this is somehow a cross-sector view of the electricity sector. When we think on data, you will have data from other sectors that are becoming very relevant for the energy sector. One example is the mobility sector with electric vehicles, but we also start to have flexibility from industry. We are starting to have flexibility from data centers. So there are a lot of other sectors that traditionally were just consuming electrical energy, but nowadays they are becoming much more active. And this view in this architecture is that you have the energy as a sector is interacting with other sectors like gas, water, transport, health, buildings, and data management platforms are somehow in between the two. So we see, for example, here, big data tools, privacy preserving tools. We see interoperability with ontologies, with common information models, with the traditional data formats like CSV, XML, JSON formats. And this is somehow as a middleman between these other sectors and the electricity sector. And on the top, there is also different data governance models, big data models, data analytics, different roles like data providers, data consumers, data managers, data aggregators. This view that is starting to emerge in Europe is a view where you have a continuous integration of other sectors with the smart grid infrastructures in a way that you start to have a full exploitation of flexibility from the sectors, data from other sectors, and so on. And that's one perspective. This is a reference architecture in Europe. Something that is also emerging in parallel to that reference architecture is the common European data space. A common European data space is a technical of infrastructure where you have edge infrastructure, services, you can have cloud, high performance computing, AI, testing and experimental facilities. And on the top of that, you have data that is shared by different data owners, different data providers, data aggregators, data consumers, service providers within a single data space for each sector. I will show you an example for energy, but these data spaces, they are emerging for healthcare, agriculture, finance, culture. So you can find a lot of data from different museums in Europe on this cultural data space. And the same is being applied to energy. Just to show you an example of an energy data space, this is an European project where we are partnered, the EnerShare project, and you have there the website to the project where you can find more details. But what we are building in the project, we are starting by having different pilots that are different data hubs, different data market platforms and marketplaces. And then on top of that, we have a data connector. So it's a critical component of the data space that allow you to get this data considering interoperability and trust. So you can, for example, define the governance model for the data you are providing, the sovereignty of this data. If you are a data provider, you can define who have access to your data, how they have access to your data, and in which format they have access to your data. And so on the top of this, we have this layer of interoperability that it's mainly based on ontologies, and also the trust, where data governance, traceability of data, and certification is very important. And then on top of that, there is the data value layer. So we are working on data markets. I will show you some examples of the research we are doing. But the idea on the project is you have a common marketplace, peer-to-peer common marketplace, where you exchange data, you exchange services, you exchange assets, you exchange energy, not just electrical energy, heating, you exchange water. So in this common marketplace, you handle data like any other asset of commodity. And on that marketplace, you can have access to those services that are based on the data that is available in the data space. And finally, on the top, we can build an energy data ecosystem where you have services that are provided by different actors and different entities. Something that is important to highlight here is that we are starting to have new actors like data space operator, data brokers, data service providers, and developers. So these are actors that normally they were not in the energy sector, and they are not from the energy value chain, but they come from the data value chain. So this is something that's being done. We are setting up all these components to build a data space, and we have energy services from the energy sector, but we also have cross-sector services. Just some examples of cross-sector service is to use the data you collect from smart meters to generate alarms for healthcare services, for example, for vulnerable people. If they're alone at home and you see a change in energy consumption, you generate an alarm to a caretaker. That's one example. Another example of a cross-sector service is building renovation and comfort. So if you want to retrofit a building or renovate a building, you can use data about energy consumption and comfort to better define the actions you have to do to renovate the building. But also, if you want to have financing to this renovation, you can also leverage on data in terms of energy consumption. So this is some examples, and going in the cross-sector direction is something valuable when we talk about data. So on this presentation, I will go through 8 use cases. Those 8 use cases will have 3 on renewable energy, another 3 on control rooms and operation of the electrical grid, and then 2 I put here at the community level. So we are talking about end users and citizens, and talking about, for example, of low voltage state estimation and control at the community level. We'll cover these big data scenarios, but in some cases we have scenarios with data scarcity or where you have privacy barriers, which is quite common nowadays. In Europe, for example, there is a legislation on data protection that is quite restrictive in terms of data sharing of personal data. And we are also starting a legislation that is called the AI Act. That is also very demanding in terms of use of AI algorithms, security of AI algorithms, and it's asking for transparency in AI. So that's also something that will change the landscape of AI in Europe, and also the way we do research will be also impacted by that. So these are the 8 use cases. I'll go through my presentation. I will show examples of each one and the publications where you can find more details. So let's start with the generation use cases. So these are 3 use cases we defined for renewable energy. And I will start with the one that I have been working on renewable energy forecasting since 2006. The focus here will be the work we published in this paper. This was in 2017, and it's a very good example on the use of big data for renewable energy forecasting. What you have here is one PV power plant. This one is a PV power plant. It's actually on the rooftop of Inefitec buildings. It's around 15 kilowatts. And what you have here is a wind farm located in North Spain. And around it, you see these small points. these small points, they are numeric weather predictions. So we have a grid of numerical weather predictions around these renewable power plants. And when we look at these grids for wind, we have 2,700 variables for the wind power plants. And for the PV side here, we have around 1,000 variables. So this is a lot of information in terms of variables, and this is a very interesting case for feature engineering. And the challenge is how much information you can extract from this raw data. So the grid have this coverage in terms of kilometers square. So it was quite big, but the resolution was 4 kilometers. That's also why we have all these variables and all these points. The data set for solar is open. So you can find it on this link in this website of INESC. So you have there the PV observations in terms of generation, and you have all these grid of numeric weather predictions. The data set for wind is not fully open. We are using the Sotavent wind farm. Their data is open, but we don't have it in the website because we weren't sure if we can actually have it from the legal point of view, and that's why you only find there the solar PV data set. So we start with this, and if we don't have so much information, I put here an example. So this black line you have here, this is the real power, the observed power from the PV power plant. And the red one is the forecasted global horizontal irradiance for the PV power plant. If you don't have any more information and you use a machine learning model to forecast the power just based on this variable, this red variable, you will have a lot of problems. For example, here is telling you that you'll have a clear sky day, and it's not. Here is telling you that you have a clear sky, but you see clearly here is not exactly clear sky. So in the beginning of the day was somehow an overcast day. And then here is telling you this is a clear sky day, and it is, and here is telling you it's a clear sky, and it is not. Okay, so if you just use the variable, and this variable is the forecast for the blue point you see here. So we are just looking at the blue point. So if you use only the information on the blue point, you'll have some forecast errors that are quite large, and so we will not have a very good forecast. What we started to have was just temporal information. So we are still working with the blue point, so with the local information, but here we have the variance of the variance along time of the forecast. So you have here the variance here, the variance here, and you can start to see that in some days it's already telling you that you might not have a clear sky day. But nevertheless, this is still not enough. The amount of information you have to the model still not enough. We are just working with the temporal information. And then something you can still have, because when you make a forecast, you make it 3 days ahead, for example, and you can make it 2 times per day, 4 times per day. So it means that for each day, you can have 3, 6, 9, 20 different forecasts. What we included here was the past forecasts that are the ones in gray for those days. And this is additional information that can be included in a machine learning model. And then you start to see that from this point of view, this is for this day in particular, this is a clear sky day. It's what the past forecasts are telling you. The past forecasts are already telling you that maybe this day, this is not a clear sky day. You're starting to see here some clouds, and the same happens with others in here. So by adding this local information, I'm just using temporal information. So just for you to understand, I'm still working just with the blue point you have here, only with that. So by adding this temporal information, we are starting to give more information to the model, but it's not enough. And what we included in the model was the spatial information. And now we are working with all those grid of numeric weather prediction points. And then you see this is a clear sky day. It's clearly a clear sky day. you see that this is an overcast day. This is the spatial information is providing you much more information, and the same in others. And then you see here also this ramp that you can see it here. Okay, so this is, by including this spatial information, you are providing them with much more information. But using all those 2,000 variables is not practical, and it will not give not be practical to include the machine learning model. So what we made was feature engineering. From all those features, we created standard deviation in time from the global horizontal irradiance for the location. We made the average of the past forecasts for the same day. We made a spatial average, so there was an average of all the spatial information. And then we have the spatial standard deviation. So using all that information, we calculated the spatial standard deviation. So we constructed a lot of features from all those 2,000 variables. So we went from 2,000 variables to 20 variables. We went from 1,000 to also to 20 variables. And that was our information to include in the machine learning model. So in the end, our model chain was the temporal features with the point forecast, was the spatial features that we extract from the spatial grid, and then we fed a gradient boosting tree with all these engineered features that we extract from all that data. And in the end, we have the point and the probabilistic forecast. So it was a simple model chain. But most of our work, and the most important part of our work, was exactly on this part. And this is where we spend 80% of the time trying to improve the accuracy of the model, because the gradient boosting tree, it's already a very well-established model for renewable energy forecasting. And if you look at the competitions that have been, they were made in the past, a lot of competitions on renewable energy forecasting, tree-based models were ranked almost all in the top, in particular for wind power forecasting. So that was our approach, and you see here an example of a forecast. So you have the point forecast is the red one, the black one is the real value, and then you have the 90% forecast interval. And this is just with temporal information. This is with temporal and spatial, and you can look at the clear sky day. So this is a clear sky day, and you see that only with the temporal information, the point forecast never goes to the top, never reaches the maximum. And then when you look at the size of the forecast interval, you see that this forecast interval, when you include spatial information, is much more narrow than the one you have here on the left. Let me change and use the pointer because it's better. And you see this behavior everywhere. So the same here, this is a clear sky day. When you look at the size of the forecast interval, is much larger than the one we have with the spatial information. When you look at the point forecast in red, it goes almost to the maximum, while here is below the maximum. So by adding all this information to the model, you are improving the uncertainty forecast, you are improving the point forecast, and you are making a much sharper forecast intervals, which is something that is really important in renewable energy forecasting. That was for us quite impressive, and these are the results for PV, but for wind they were similar. And to show you an example of the improvement, so this is the improvement, and we are comparing the improvement over this model. So this model we're using chronological variables, was using the short wave, which is the global horizontal irradiance temperature, and cloud cover at different levels. This is our base model, and the improvement you see here is over this base model. And when we have temporal information, we are only temporal information, we already had an improvement on average for the mean absolute error on around 13%, and root mean square around 10%. The continuous ranking probability score is to measure the quality for uncertainty forecasts, and you see with the temporal information, only with the temporal information, we already get an improvement. With spatial, only with spatial information, we get a similar improvement. But when you combine both temporal and spatial, you see an improvement in the forecast error. So you go from around 12% up to 16%. So local and spatial information together, you see a big improvement in the accuracy of renewable energy forecasting, in this case on PV, but the same is applicable to wind. So that was one work we made. This is integrated in some commercial forecasting systems, not just for wind and PV, but also for load. And that work was also other companies that are doing forecasting were also influenced by this work. And then we started to think also in 2017 on this idea of combining data, in this case observations, from different PV and different wind farms geographically distributed. So imagine that you have different observations from PV plant 1, 2, and different. We can have 200, 300 different plants. You have the sequence of the observations, measured observations. And we started to use this vector autoregressive model. So this is a very simple model, a linear model, where you forecast the generation of site 1 and 2 as a function of the past values of those sites 1 and 2. The limitation here is that you are sharing data. So if site 1 and 2, they are competitors, if you start building this model, you need to have access to data from your competitors. That's one limitation. Another limitation is that this is a linear model. And we know that in wind, the relation between wind speed and power is highly nonlinear. In PV, it's a little bit linear, but when you start to include temperature and cloud cover, it's no longer linear, and linear is just an approximation. So that's another limitation. So one thing we addressed was data privacy here. What we wanted was that you can build this model, you can use this model without having access to this confidential data. That was the primary requirement. And the second one, we used the additive models to capture the nonlinearity. So additive models is quite well known in the literature, and we just use it here in the VAR model, in the vector autoregressive model. So that was our framework. And why this is interesting, because we are starting to have a lot of new data that is geographically distributed. We have PV panels geographically distributed, wind turbines, smart meters, smartphones. You can use data from crowd sensing from smartphones, electric vehicles that are always moving. So that's also always something that you need that data if you want to operate the grid and know when they will charge. Assets like power transformers, Internet of Things is bringing more data. The barriers, data privacy and confidentiality. So either the data is personal data and you have a lot of problems, as I mentioned in the beginning. In Europe, you have to pay financial penalties if you don't comply with data privacy, and also confidentiality. Some companies, they simply don't want to share their data. And then there is a lack of monetary and non-monetary incentives for data sharing. We'll go there in a few slides about the data market concept. And then there is also a lack of business cases for collaborative analytics. So that's the main barriers. To solve one barrier, we developed this privacy preserving protocol, or a federated learning protocol. This was published 2 years ago in this paper. So going back to the example I gave, you have three different sites. They don't want to share data between them, but you have to build this VAR model where you have lagged power observations of the 3 sites. So if you just present what you have here to them, they will say, no, I'm not interested. I don't want to share or combine my data with my competitors. What we made with Algebra was some kind of a data encryption based on Algebra using ADMM, alternating direction method of multipliers for distributed computation. And there were 2 key ingredients here. One was data encryption, power data encryption matrix that it's unknown, but built by all the agents. So all the agents, they contribute with their own matrix, but agent 1 only knows his matrix 1 and does not know the matrix of agents 2 and 3, data owner 2 and 3. And this is randomly generated, this matrix. Okay, and this matrix is used to encrypt the power data. And the second ingredient is the random matrix to encrypt the coefficients. So when you do this, what you get in the end are encrypted coefficients. Then you run ADMM with data fully private. You get the encrypted coefficients, but then you need the original coefficients. So each agent owns a part of the key. So each agent owns this random matrix, and he does not share it with all the other agents. So with this, we are able to work with confidential data or private data, break the model fitting problem using ADMM, and it's completely robust against any kind of data breach in terms of privacy. And we have a paper, is not here in the references, but we have a paper where we show the limitations of the state-of-the-art approaches. And in this paper you have here in the reference, we show proofs that this is robust in terms of privacy. So that was our approach. You will see later that this can be applied in other use cases. By doing this, and we apply this model to 60 wind turbines from 30 wind power plants in France by using ECMWF model. And you see here the improvement of the collaborative approach over the univariate approach. So on average, we can get an improvement of around 5%, but the maximum can even be above 10% in terms of improvement. Of course, that not all the wind turbines and not all the wind power plants have a positive improvement, so some of them do not benefit from this collaboration. And that's something also that it's an important remark and we need to have in mind. And then we compare our VAR, our additive VAR or additive model VAR with the gradient boosting trees using exactly the same input variables. And the goal was to have at least the same performance, because the thing is, data privacy was our concern, and we want to have a model that has the same performance as the state-of-the-art model in wind power forecasting, but at the same time it guarantees that you have data privacy fully guaranteed. And you can see that on average, actually the performance is slightly better than gradient boosting trees, around 3% on average. And that is, for us, a very interesting result, because we were just targeting exactly the same performance, because we're using exactly the same variables. So that's this work we made with this multivariate time series forecasting, in this case for wind power, but we have other publications for PV. And you can find the data set on this website in ESCTech. You have the data set for PV, that is, I think, around 60 PV time series that are geographically in the same area and can be used to test and develop similar models to this one. So I mentioned new privacy. One thing is that data owners, they want to improve their forecasts. They would like to use all this data, but either you have to compensate to provide you the data, and you have to create some kind of incentives. Something we are working in, we started to do this in the Smart Forecast project, and we are working now in two new projects, Enershare and Green Data AI. We are working data markets, so data by money. You provide data and you get money in exchange. So the monetary compensation in this case is proportional to how much your data, the data that you are providing, improves the forecast of the one that is buying your data. So it's exchanging data by money, so it's data monetization. In Enershare, we are also we're also developing in data by data. So you provide data and you receive data. There is no money here involved, but you have to guarantee that the value of the data that you are giving, it's the same value of the data that you are getting within a tolerance. This value can be measured with mutual information, correlation, and so on. So if you are using data from someone else to improve your classification model, you need to give data to that one with the same value to his model like it has for your model. So that's the approach. And the third one that we want to do, but so far we are not working on it, is data by recognition. So if you provide data for the common good and your data have a positive impact on something, you could be recognized not in monetary terms, but you can get the recognition that your data is helping to reduce CO2 emissions because of better operation of a PV system, for example. So these are the three frameworks. Right now we are more advanced on these two frameworks, and I will show you an example for the data by money. So on data by money, this is a paper we published also 2 years ago, more or less. It was, I think, one of the first papers on data markets for renewable energy forecasting. And the idea is quite simple. So you are a data seller, you are providing your data, you want to monetize your data. The revenue of your data depends how much your data contributes to the buyer in terms of improving the forecasting skills. So if you have a certain variable, you are providing me that variable, and my forecast improves. Because of that, I earn more money in the electricity market. I divide part of my gains by paying you the variable that you provide me. There are two challenges here. One is how you allocate these gains. It needs to be in a fair way. Another one is what are the offers. So what you make as an offer together with the data. So is a price, is a value, is a price and a value. So these are the key questions here. One version we develop of this data market, this is one algorithmic solution. Actually, we have right now 4 algorithmic solutions for data markets. So imagine that you have three data providers and data buyers. We open a market session. On that market session, each one of them, they make an offer, they make available their data. They say what is the minimum acceptable price for selling their data. And if they are buying data, they also set what is the maximum acceptable price for buying data. This is similar to what we have in the electricity market, where you make a bid with the minimum price you're willing to get and with the maximum price you're willing to pay for electricity. But here we include also value functions. So in addition to the prices, you have a value function that is a function of the model. It tells you how much valuable is this data to your model. I will show you an example of it. And when we close the sessions, we got offers from the three, data, prices, and how much value you put on the data. And then we dispatch a market to maximize social welfare. In certain sense, is like an electricity market operating, and so in the end, you get a common price for all the data that is being exchanged in the market. So this is one approach, and you basically maximize the sum of the value function for the sellers plus the value function for the buyers. So social welfare maximization, and that is one approach. We apply this to a simple case. We had here 5 control areas in the North Pole market, actually with wind blowing more on this direction from Denmark to Sweden. So we defined there a minimum price of 40 cents and 100 cents for the maximum price. And then there was 2 value functions, exponential and linear. So exponential means that more you are approaching, or more improvement you have, more you are valuing the data you are getting. And we also included the value function for the seller that is related with how much your data is being used in the model of the buyer. So if the buyer if your variable that you are providing is quite valuable in the model of the buyer, you'll get more value in your data as a seller. I think the interesting thing here is that these allow both data seller and data buyer to understand and put a price on the top of the data they have. And that was something interesting. When we look at the results by running this market during a historical period, we can see that some of the data buyers, they have a big improvement on the electricity market gain. So this is what you see here is improvement. So we have here one agent that have a big improvement on the electricity market gain. Is also paying more for the data, but is also getting some compensation by the data market. So actually the gains of this agent is this improvement in the market bidding plus the data compensation. Some agents, like you see here, this agent does not have a big improvement, and most of the improvement is by selling his data in the market. Of course, this is different variations considering the different value functions that we have here. So that is the main outcome. You can see that some of the agents like this one, after some time, they will not participate in the market because they are not getting any kind of they have a negative improvement by bidding in the market because the forecast is not improved so much, and they're actually paying more for the data than what they get. So there is not any incentive for these agents to remain in the market, and some agents they might leave the market. Okay, so and then we develop a prototype. What you have here is a prototype that is using IOTA, so a cryptocurrency of the market. And this prototype is like a electricity market. So you have an open market session, you place bids, you get some kind of payment confirmation to check if that agent have money to pay the data later. You close the market, you run the market clearing, and then you distribute the payments. So you dispatch the market and you distribute the payments. The only thing we are using blockchain is only for the cryptocurrency. You can see these slides will be shared, and then you have this link on YouTube, and you can see a demo of this market. So you will see a demo of the market running together with the algorithms that are in the backend, and you see agents trading their data. We are further developing this prototype, and we hope, and that's on our plans to make this open source. And there, together with open source, there will be different versions of the market, and it can also be some kind of a playground to test different data monetization algorithms, or even data by data algorithms. And the second use case on renewable energy is trading, so market trading. So we have, if you look at the literature, typically you have these price forecasting algorithm, renewable energy forecasting algorithm, and an optimization algorithm, and in the end you have an optimal trading decision. The problem of this is complexity. You have here 3 models, but if you look at the prices, you need the spot price, the imbalance prices. If you are considering reserves, you need a 3rd model, so you can easily have 6, 7, 10 models here in this model. So this is a huge complexity in the model chain. And then you don't have any kind of explainability. So this is like a black box for the human trader. One option is to on the top of these, you can use some kind of explainability, and you can try to explain why this forecast was like that, considering the input variables and so on. So explainability would be something to add here. But it might not be enough, because we still have this complex model chain. So you have to explain this model, and this model. So for a human trader, this is not very, very effective. One option, and this is what we are doing, is you have a single model, so it's a prescriptive model. You just use weather predictions, observation as input. There is no forecast here. So you feed the same data you use for forecasting, and the model outputs directly an optimal bid. Okay, but on the top of that, even if you have a single model, you need to have offer some kind of interpretability or explainability to the human trader. That's another challenge. One option of explainability, you can use, for example, Shapley values. They have been used a lot in machine learning. They give you feature importance, but they are called post-hoc methods. So you go to a black box model and you try to explain why this black box model got this output and this decision. In our opinion, this is not enough. And what we are doing right now is a symbolic model. So you have, again, a single model, but you don't have a neural network or a gradient boosting tree or anything. You have a symbolic representation if you're trading rules. And with that, you can easily reasoning. A human trader can look at a symbolic model, can modify it, can understand it. There is no need for these post hoc techniques. So 12 years ago, we published this paper 12 years ago, where the idea was to feed a neural network with this input data, wind speed forecast, temperature forecast, total cloud cover, and the output will be a trading decision. So there was no forecast in the middle. So you're using input data and the output was already optimal trading decision. So this was 12 years ago. Right now, we have been working on this approach where you have a symbolic model, so a set of equations and rules that tell you how much you should trade. And we build this symbolic model in the same way we were building the neural network, but instead of a neural network, you have a set of equations, and equations that an operator can understand. So I will show you an example for PV or for wind. So we are growing this model by using genetic programming. So what you see here is the method of genetic programming. This is similar to genetic algorithms, the typical genetic algorithms. This was something we published 1 year ago, but the mutations you do is on the tree, and this tree is equations. Each tree represents an equation. Each member of the population is an equation, and then you do these mutations by changing terms and mutating also terms from the equation. The rest is similar to genetic algorithm. By doing this, what you have as a model are these trees. So it's an equation, and you can optimize any reward function to maximize, for example, the profit in the market. And this is basically what we do. We are a model. So we are optimizing a reward function that is the imbalance cost. So we want to minimize the imbalance cost from forecast deviations. And we are using this genetic programming to build this symbolic model. But we found also that it's important to cluster data. So we will show you results without clustering data. And in here we show you results where we have low wind speed, medium wind speed, and high wind speed. So clustering data can be very important. This is the output of the model. So imagine that you are a trader, and the model are these three equations you have here. If your forecast wind speed is low, your optimal bid is this equation. If your forecasting wind speed is medium, between 4 and 11, this is the equation you should use. If it is high, this is the equation you should use. And those equations are exactly what you see here as curves. And this is quite important because you can easily make an interpretation of these equations, and you see that temperature, they have an effect on the model and on the offer you are doing. And the cloud cover the same when the wind speeds are high. So that's this model is something that any human trader can understand, can improve it, and can include his own knowledge on it. And what we made here, we divided the data by these three areas. If we don't divide the data by the three areas, we get this model which is simply doesn't make sense. So data partition here is a very important step to consider. Okay, these are results from the model. We can outperform the reference model that is analytical model, the optimal quanta. And you see here those results. So we were quite happy with these results, but we are working in new approach, similar, but I think much more advanced, and we actually have to submit a journal paper this week with that. And the results are much more interesting, and the approach is much more complete. But I think to show you the idea, this is a good example. Last use case for renewable energy, digital twin for operation and maintenance. We had this project, and you can find the publication here from PowerTech this year. So we basically, in MATLAB Simulink, we created a digital twin of PV power plant with a particular emphasis on the inverter. So the inverter was very well detailed, and this is the component that creates more problem on PV power plants. 80% of the unavailability of PV power plants is because of the inverter. Okay, so that's another thing that it's important. So our emphasis was on the inverter. And we wanted to classify the types of faults you have in the inverter on the PV power plant. And for that, we generate data, synthetic data with the digital twin. We again use feature engineering. We created a lot of variables from that raw data, and we were combining synthetic and real data. Synthetic data was used to create, with the digital twin, examples of faults that either you don't have in the historical data or you have a low number in the historical data. And then we created variance and mean from these features. And we fed these on our machine learning pipeline with hyperparameter tuning, different machine learning models that we wanted to compare. In the end, the problem was the multi-class classification, and we want to classify 5 different types of faults in the inverter, and that was our main goal. These are some of the results, and you can clearly see here the value of feature engineering. So we went from the accuracy of 96.7 to 98.2, but even the type of classification errors that we were doing, it was different. And that is very interesting. So with feature engineering, you can improve it. And you can see that we have a very high accuracy in classifying the faults of inverters. So in practical terms, every time you had the unavailability of an inverter, a problem inverter is not operating in the PV power plant, with this approach, you immediately classify the type of fault, and then you can know which component to replace and what we do in terms of maintenance. Right now, we are working in the location of the fault. So big PV power plants, they have several inverters and PV panels, streams of PV panels, and locating exactly where is the fault is a very important problem, because they are over a large area. So searching for a fault is not straightforward. So that's one application. Yeah, I don't know if there is any questions. If not, I will move forward. We still have some use cases to show. Now I'm going to system operation use cases. And on system operation use cases, I will start with the control room alarm management. Nowadays, human operators at control rooms, they are getting a lot of information, and they are getting a lot of alarms in a few seconds. So you can easily, in 1 minute, you can easily generate 200 alarms. This is becoming more problematic with more renewables and with more sensors in the network. More problematic this is. And this is something that at a certain point the human operator will simply break with the stress level, and they will make poor decisions, and they will not be able to make any kind of decision. And this is an issue, and we have worked with real data from the distribution system operator where this scenario is actually critical. This is one example of this data. It's in Portuguese, but yeah, I think you can understand this is a set of tags that are the alarms. It's from the Portuguese DSO. And what you see here is alarms in 1 second. So in 1 second, you have 40 alarms of an event, and this is not complete, okay? In 1 second, I underline that. And this falls in the problem of relevant data. So we have 8 million historical records of alarm. From those 8 million, only 10% were relevant, and they were useful for us. So this is not big data, this is a relevant data. You have to find the relevant data in the middle of more than 8 million historical records of alarms. And for that, data representation is quite important. So we published this paper last year, and this is the original sequence of alarms, and we compare different approaches to represent the information that you have on this alarm. Integer encoding, one-hot encoding, TF, IDF was the most interesting one that is used also in text mining. And when we look at the advantages of this approach, they were simple to implement, low computational effort, but there was a problem. There was no information about the sequence. They were analyzing each tag individually. So they were looking at this one, this one, this one, and this one, and not the whole sequence. And that was a limitation. To solve that limitation, we use the word2vec. So we're working with embeddings. This is quite common. ChatGPT is using this a lot in large language models. And basically, we convert this sequence. We use this as an input to a neural network, and we use the hidden layer of the neural network as an embedding for that sequence. And this is what we use in the rest of the machine learning pipeline. The major advantage of this one is that it captures the sequence between tags, which is quite important information, but computationally is very intensive. So you require a lot of computational power, which is not, in my opinion, the ideal, and is very time consuming. Another representation, and this is a paper we have under review, it's actually taken a lot of time to get the reviews, is a graph-based representation. So this is somehow like a knowledge graph. It is a collection of all the alarms for short face-to-face cases. And with these, you see the transition, the black lines are the transition between phases, like fault detection, isolation, recovering, and operator action. And the blue ones are the most frequent actions, and the red ones are the, let's say, strange ones or rare ones. And with this approach, if you show, this is making a summary of millions of alarms and records. If you show this to the human operator, he knows exactly that on these events, something strange happened. And then he can look more into detail on those events. So this representation visually is interesting, and we are also using it as an input data to a machine learning algorithm. That is exactly what we have here to classify the type of faults. One application of this approach we have here is to identify abnormal protection behaviors. So that's also, you find these on this paper. On that paper, with real data, we found to this distribution system operator protections that were not operating properly, and they were classified as uncommon or rare. And the approach was quite similar. Quite simple. You get the current context, so what you are observing now in terms of alarms, you compare with historical context using cosine similarity. And so you have the similar context, and then on the similar context, you see which tags are common and rare by using the TF IDF. What was for us quite difficult was exactly how you do this encoder. So that's what I present in the past slides. Data representation here was a big challenge. Another interesting application is when you have a fault on the grid. This is between two primary substations, everything is open. And the human operator, you have a lot of pressure to restore power immediately. And so what he does is he do a trial and error. So he closes this one, he closes everything, and then he opens again, then he closes this one, and he opens again, and it's a trial and error until he finds the solution, or he gets information about the location of the fault. This trial and error is a lot of money and time, and so they can, if you provide them with the fast advice, they can save a lot of time and stress. And we use this idea of encoder-decoder again, and we were converting the alarm data into a sequence of actions. So this is similar to what is used in translation of speech. So you translate a sequence of alarms to a sequence of actions. We have this published in the MedPower conference last year. You can find the paper with the details. And that was interesting because, so this is the situation, everything open, and you want to say to the operator which reclosers, automatic reclosers, it should close, and which one it should leave open. With our approach, we have analogous search, analogous situation, the encoder, decoder, you can tell him, close these two and leave these two open. And if you do this, and if we are accurate, we save a lot of time to the operator, and we can restore the power in some consumers. Of course, we still have to keep this open because the fault's still there more quickly. One interesting conclusion, because we don't have so much time to go into details, but one interesting conclusion is that the encoder-decoder model had a good performance when you have more data, and the performance was not so good where the number of episodes and data was lower. And the cosine similarity was exactly the opposite. But cosine similarity was very computationally intensive when we are using the model, because you need to find similarities in the whole historical records, and the historical records, again, are millions of records. But we found this interesting because it seems that these deep learning approaches, they work pretty well when you have a lot of data. When you don't have when data is scarce, they are not the most accurate approaches, let's say. Okay, another use case for control rooms. This is something we published 4 years ago. And this is data collected from the PMUs. They are located in Brazil and in South America. They collect one measure at 1 divided by 60 seconds, so 60 measurements per second. And you see here, these are the types of events that occur in transmission networks: generating tripping, line tripping, oscillation, and load shedding. And the goal was to classify these events based on PMU data. If you look at these, you can distinguish these, but what we wanted to do was to represent these events as a frame. So we convert these events you have here in time in the frame. So instead of having this evolution in time that was also a lot of data, you summarize everything in one frame. And if you look at the frames, you can visually distinguish generating tripping from load shedding, oscillation, and line tripping. So you have a visual, completely visual separation of the four, and this is, and you summarize also data. So again, like I was explaining for alarms, this work and this problem was a lot about data representation. That was an hot topic some years ago, but nowadays no one is concerned with data representation, but it's quite critical. The performance of machine learning depends a lot in the way you represent data. So then was to classify the results. Again, the goal was to classify the type of faults. When you look at this matrix, you have different types of faults, and you know how they are because you see here oscillation. This fault will be oscillation, and you can easily distinguish it. If you feed a convolutional neural network with this information, it will make a good job because they are very good in distinguishing and separating these kind of events. And this is what we made, and we got 100% accuracy. Of course, we have to use NVIDIA GPUs because it's very intensive, but this representation combined with a convolutional neural network gives you a perfect accuracy in classifying these events. And this is using real data from the real large system, the Brazilian power system. So this is not synthetic data. We separated well the validation set, the test set. So these are real results. Third and final use case on the power system operation. Something we have been doing, and this was accepted for publication this year. You can find it online. Was imagine that you have a probability of a congestion for the next day, and you have to decide if you reserve a flexibility option, a flexible resource now to solve the congestion problem, or if you wait for the next forecast. and you have multiple forecasts along the day. So you are now here at 0, you have this forecast, but you know that 6 hours later you have a new one, and 2 hours before the hour where you have the forecasted congestion problem, you will have a new forecast. The question is, should we decide now or we wait for the next forecast? So should I decide based on this information, or I wait 6 hours and make a decision there? The problem is that uncertainty decreases with time, in theory. So this will have less uncertainty than this one. But if you have a shorter notification time for flexibility, the price will increase. So if you tell a consumer that will be you curtail his consumption 2 hours before that, you have a price. If it is 1 day before, you have a lower price, of course. So that's the challenge. What we made was what we call second level forecast. So at this time, we were generating a forecast for delivery hour, and we were forecasting this forecast. So it's like a meta forecast, where it's a forecast of a forecast. So here we are generating this normal forecast and 2 second level forecast of a forecast. And based on that, we build risk cost curves, and then we can make a decision based on these 3 cost curves, because the price that you have a forecast of the price it will cost, you have a forecast of uncertainty, and then you know if you should wait, if compensates waiting or not. That's basically the idea. Second level forecasting was a challenge. Again, here we created feature engineering, we tested gradient boosting trees, and we use also the encoder-decoder. Like I showed for the alarms, what we are doing, we are transforming one forecast in another forecast. So the second level forecast is a decoder part. And we compare with the baseline model that is like a naive model where we assume that the forecast does not change. If you don't outperform this model, it's garbage, the model you are developing. And you could outperform this model between 13 to 26%, 31% in the Minnesota. I think we were happy with the results. And by using these in this decision problem, we see that we are saving a lot of flexibility. So the operator is willing to wait when it's a good decision to wait, and in some cases even don't need flexibility because there will not be any congestion, and the forecast generated 2 hours before detect that. So you can see the paper for more results, but we were happy in showing that this is a very interesting strategy and can actually save a lot of flexibility costs to system operators. Okay, now going to my last two use cases of this presentation. I have here the smart meter analytics use case. So this means we are working here with smart meter data. And the first use case is to identify consumer elasticity or measure consumer elasticity with causality. So if you are an electricity retailing company, and if you want to offer a customized tariff to a consumer, this elasticity is quite important because you can design a tariff that matches the expected behavior you want in terms of demand response from that consumer. Or if you are using already demand response products, you want to know the reliability of the demand response. If you tell a consumer that the price will increase 10 times, you want to know how we will react to that information. So the objective for us was to estimate the consumer elasticity and also to rank the consumers according to their elasticity. And for that, we use causality analysis. So we start with price signals, and in this case was a time of use pricing with critical peak pricing. That was displayed to the consumers in the home energy management system, and we're using causality inference to know exactly of what was the consumption elasticity of that consumer. You can see this on this paper that was published 3 years ago, and allow us to estimate the reaction of the consumers. And this is details of the causality algorithm using the Robin G method. And I think here, and it's important, we are not just using the tariff information, we're also using information, exogenous variables like the weather condition, the ambient temperature inside the house, the day of the year, the day of the week, the day of the year, the month, everything. So we were using also a set of explanatory variables that together with the price allow us to make a causal estimation of the impact of this tariff in the consumer profile. These are the results, and those results they are interesting. We have made this for the low price tariff, and here you clearly can see what are the consumers who have more elasticity, and also along the day, 24 hours of the day, when they have more elasticity. So these consumers will have less elasticity. These will have higher, but some hours of the day they don't have high elasticity, and that was one outcome. And we made the same for the high price tariff. We are using the low carbon London data set, and the low carbon London data set, they have normal price, low, and high price. So there are only three prices, and that's why you see this here. So, but you see that which ones are prone to low prices and which ones for high, and you can see that they are not the same ones. So there were consumers with more elasticity when the price was high, and others when it was low. Sometimes it depends on what kind of lows they have at home or not. Okay, so that was one problem. And another interesting result that we made was exactly to measure the performance of this demand response program. So we were able to see the ones from the total of consumers, the ones that are more elastic. And you can see that from the 81 consumers, around 25% of them were top responsive clients. So this means that this demand response program was only being followed by 25% of the total consumers that the retailing company had. So you could change the demand response program trying to get more consumers with more elasticity. So that's an application of the causality analysis that is also quite interesting. And finally, in my final use case, also to have some time for questions. Low voltage grids, they are the major bottleneck in smart grids. We have all these resources, and all these resources are creating technical challenges, and also the DSO is installing advanced metering infrastructures. They are getting more data, and so we could assume is the situational awareness of the low voltage grid improved by the smart meters? And the answer is still have a lot of limitations for traditional state estimation methods. So they have observability issues, low redundancy in terms of measurements, numerical stability in some cases, but most important, there is no accurate information about the grid topology and the parameters of the grid. And that is a strong limitation. And also the real-time monitoring of the voltage and active power is not available. You have technologies, communication technologies, but they cannot get data in real time to the control centers. Our idea was to use historical data that we collected from smart meters together with a few smart meters with real-time communication, and it was to estimate the full operating condition of the network. This is an example. Imagine you have this low voltage grid. We have a few meters with real-time measurements. So every 15 minutes we get active power and voltage from these meters, and we use a state estimator to estimate the voltage and active power in the meters in blue. That's our approach. Our approach, you can see it, this was presented in PSCC in 2018. It's simple. It's basically we search for analogs in the past. So you observe information from the real-time meters, exogenous variables, you go to the past, you make a similarity analysis, and you pick the ones that are more similar. This is our approach, and we have, of course, a smoothing process because we compare different similarities. We test these in three real low voltage grids in Portugal. One with the three with more than 100 consumers with different assets. And we integrated these with Power On Advantage from GE, from General Electric. So this, and then we only have 10% of the meters with real-time communication, so 15, 18, and 12. So this means that more than 100 consumers didn't have real-time measurements from their meters. And these are the results for voltage and for active power. And we got very accurate results, both in voltage, both in active power. Voltage is more easier to estimate, but only with 10% of real-time measurements, we could have a good picture or a good snapshot of the low voltage grid operating conditions. So that was one of the achievements we had in this work. And again, this is a real environment, real consumers, real assets, real data. So it's not a simulated result. And finally, we are monitoring the grid, but then if you have a voltage problem and over or under voltage problem, you have to solve it. And there was this paper published by Vito in Belgium several years ago, where they show that you can use a regression model to extract the sensitivity indices. So they do a regression model where you have voltage, when you have power, active power, and the X voltage in the I, and you simply take the coefficients from the linear regression, and they are the sensitivity indices. So that was their approach. They published this. In our case, in the paper we published last year, we started exactly the same approach. So we get the sensitivity indices, taking directly from the regression model, but there was a problem. When the grid operating conditions change, also the sensitivity indices change. So what we have used was what is called variant coefficient linear model, where you no longer have a coefficient, you have a function. So your coefficient is a function, and it is a function of exogenous variables. Those exogenous variables can be the transformer load, can be the voltage at the transformer level, can be average voltage in the grid. And so what you have is, instead of having a single coefficient or sensitivity, you have a function. So when the transformer load changes, the sensitivity will change as well. And I will show you this is much more accurate than a fixed approach like this one, where you assume that this is fixed. That was one problem. Another one is that smart meter is classified as personal data. So in Europe, if you use smart meter and you are not careful and you disclose the smart meter data, you need to pay a lot of money because of that. So that was the problem. And then going back to the beginning of my presentation, in use case one, we use our federated learning protocol to calculate the sensitivity indices without having access to the smart meter data. And we can do this in a centralized way by a DSO. So it can build the sensitivity indices, but you'll not have access to the customer A, B, and C data, or they can do this in the peer-to-peer mode. So both approaches are possible. You have an application of this privacy protocol in this paper, but this is basically more or less the same privacy protocol I showed for forecasting. Just to show you the accuracy for a typical Portuguese network, and I want to highlight this: if you use the constant sensitivity model, you get this accuracy in terms of root mean square error for the coefficients. If you use the variant coefficient approach, you get a big improvement in the model. Of course, if you start using a big neighborhood, you converge to the constant sensitivity model. So with this, they were quite accurate. You see, the accuracy is very good of these coefficients, and then we can plug in an optimization problem to solve voltage problems in the low voltage grid, and the coefficients are simply a parameter of the optimization problem. Okay, that's something we can do all of these with smart meter data without disclosing the smart meter data. That's something I would like to underline that. And there are also manufacturers of smart meters that are working in edge solutions, so we can run these at the edge. To conclude, just to give you my final remarks, and we'll have time for questions. When we have to look at simplicity versus simplification. In my opinion, model chains in big data and in machine learning, they are becoming complex. We are starting to have long short-term networks with attention layers, then combined with transformers. It's becoming quite complex. And my open question is the performance improving? Is the user using it, adopting it? Is industry using it? I'm not sure. Actually, I'm quite pessimistic on that. Then we have to think on explainability versus interpretability. Explainability and interpretability, they are not the same thing. And the impact of the AI Act in Europe is tremendous. So they require more interpretability and transparency. And then algorithmic version, they remains, nowadays, they still remain in the industry. They prefer expert systems, knowledge-based systems, and they have some aversion to algorithms. And then we have to create incentive mechanisms for data sharing. Just having platforms for data sharing is not enough. We have to create these incentives. And we have to advance on human AI cooperation. That is also something very, very important. You'll see this in my last slide. And finally, the communication of forecast uncertainty to humans is also an important challenge, not so easy to address as it seems. And to conclude my presentation, we have 2 new European projects starting. We're actually recruiting PhD students. If someone is interested, or postdoc, we are also recruiting. One is AI for RealNet, is application of AI to critical infrastructures and to cooperate with humans. And these critical infrastructures, they are electrical networks, railway and air traffic management. And there are different ways of cooperating with humans. And the InField project is a lighthouse project for EU, have the best research institutions in Europe on AI in Europe, and is looking at green AI, adaptive AI, human-centric AI, trustworthy AI, also applied to the energy sector. So this started, AI for RealNet started this month, and the InField started in September this year.